Good morning, good afternoon, good evening, everyone, for finding time to join this webinar. I am Professor Krishna Reddy from University of Illinois, Chicago. I am the organizer of this webinar series. And as you all know, this is our weekly webinar series. And the main purpose of these webinars are to recognize the emerging challenges and try to think about innovative solutions. And more importantly, as I said, foster the collaboration so that we can all work collaboratively. So everyone is welcome to attend this, and you can look at this link to see upcoming webinars and register for those. And this webinar series is supported by ISMGE TC215 Environmental Geotechnics Committee. So previously recorded webinars are available on the YouTube channel. You can go to that and view the previously held webinars. I will put this link in the chat box later on so that you have already access to it. So here is the upcoming webinars for this semester. So after today's presentation, we will have 3 more before end of April. So let's talk about today's webinar. As of this morning, I have about 632 registrations. So please mute your mic and switch off your video. So at the end of the presentation, I will ask you to show the video and we will have a group screenshot. And then you can type your questions in the chat box or you can unmute and ask questions. So our presenter will answer as many questions as possible. So if you need a certificate of attendance, I will be putting the link to Google form in the chat box. So you must fill that Google form to get the certificate of attendance. So it's not possible to fill it up later on. And if you need a PDH, those who are in the US, indicate that one in the form, and we will contact you. So regarding today's topic and presenter, today's topic is extremely important for people in geotechnical, geoenvironmental, and environmental field. It's enhanced contaminant containment performance of innovative vertical barriers. And our presenter today is Professor Yan-Jun Du. He is also the director of Institute of Geotechnical Engineering at Southeast University, Nanjing, China. So very brief introduction to him. So he received a bachelor's and master's in engineering geology from Nanjing University. And then he got his PhD in geotechnical engineering from Saga University in Japan. As I mentioned, he is currently a full professor and the director of the Institute of Geotechnical Engineering at Southeast University in Nanjing, China. So his research interests are, and as well as consulting works are in geoenvironmental engineering on topics such as developing novel binders for stabilizing contaminated soils and geoenvironmental properties assessment using multi-scale methods. Developing novel vertical barriers and polymer-amended bentonite-based engineered covers, liners for use at contaminated sites in impoundments, and assessment of contaminant containment performance. And he also works on sustainable geomaterials and performance-based design using them. He has published over 100 excellent journal papers. He has compiled 2 national industry technical specifications as the editor-in-chief. He also received over 50 inventions or patents in China. He won the program for New Century Excellent Talents at the university, and also he received the National Science Foundation for Distinguished Young Researcher Jiangsu Province Award. He's received many other awards also for his research, including these few of them I listed here. And He also has been elected as a member of TC 205 and TC 307 committees of the International Society of Soil Mechanics and Geotechnical Engineering. So he's also a member of ASCE GI, Geoenvironmental Engineering Technical Committee. He serves on the editorial board of Canadian Geotechnical Journal. He's the associate editor of the ASCE Journal of Materials in Civil Engineering and Chinese Geotechnical Engineering Journal. And he's also one of the advisors of Environmental Geotechnics Journal. On a personal level, I want to say that I have known him for almost a decade. He's my good friend and collaborator. I'm showing the pictures of my visit to their university in 2014. As I said, almost 10 years ago, I taught a week-long short course three times, and I collaborated with Professor Du on research projects. And some of his students actually came to my university and did excellent research. And I'm showing some pictures of not only doing the research, but a little bit socializing and showing the visiting students how good the Chicago pizza is. And also, I didn't want them to miss Chinese food. We have a great Chinatown. So I'm showing the pictures of having some fun along with doing serious research. So with that brief introduction, I want to thank Professor Yan-Jun Du for agreeing to give this webinar. And I want to thank all of you for finding time to join this webinar. So let's listen to the webinar and learn something together. With that, I want to stop sharing the screen. I request Professor Du to share the screen and start his presentation. Thanks, everyone.
Yeah, thank you very much, Professor Reddy. Thank you very much for your wonderful, excellent introduction of me. Ladies and gentlemen, good morning, good afternoon, and good evening. My name is Du Yan-Jun from South University. Today, it's my great honor to be here to present in Professor Reddy's webinar. The title of my presentation is Enhanced Containment Performance of Innovative Vertical Barriers. Firstly, I would like to thank for the graduated students involved in this research. Also, thanks are due to my long-term partner, Professor Krishna Reddy. I think our friendship started from 2030, 11 years ago. Also, the collaborator, Dr. Jin Fei from Cardiff University, and Dr. Tian Kuo from George Mason University, and Dr. Chen Jiannan from University of Central Florida. Thanks are also due to financial support from NCFC and most projects. The content of my presentation include 4 parts. Number one part is background. Number 2 is novel vertical barrier and contaminant performance evaluation. Number 3, concluding remarks, and finally, challenges and future work. First, let's look at the background. Vertical barriers are extensively used in contaminated sites and landfills to contain contaminants in groundwater and to control migration impacts to groundwater quality. Construction measures of vertical barriers generally include two methods. One is called one-phase method. Actually, it's a slurry trench method because the instill ground is digged out and the bentonite slurry is introduced into the trench for literal supporting of the trench. The excavated soil is mixed with the bentonite powder to the target moist content, and then the soil bentonite mixture is backfilled into the trench to form a vertical cut wall. So this is called actually is called excavation, mixing, and backfilling. In for the one phase method, actually is called is a mixed wall. It's mixed wall conducted with auger deep mixing CSM or TRD, whereas CSM and TRD are very advanced construction equipments. In this method, instead mixing with no or very minor shallow excavation. So all those photos are from Professor Jeff Evans, who was working in Buck University and my good friend. In US, the soil bentonite is very popular and is the main. Recently, soil cement bentonite received attention. In UK, the cement bentonite and slag cement bentonite backfills are very popular. In China, it's a little bit different. The deep mixed soil cement is mixed wall, actually, it's used to mixed wall as well as geomembrane. But recently, the SB backfill is receiving attention. Oh, my research motivation for the amended bentonite is due to uh, the sodium bentonite or sodium activated bentonite will have higher K and low swell index in when exposed to cation solutions, as you can see from the left figure and the right figure. On the other hand, the soil cement barrier will have relative high K under high contaminant concentration, as you can see from this figure. So this figure shows when the x-axis is the contaminant concentration, and I'm sorry, the mouse is not working. The x-axis is contaminant concentration, the y-axis represents the strength modulus or the hydraulic conductivity K. This is because the hydration products of cement, such as CSH and AFT, the amount of CSH and AFT will decrease with increasing contaminant concentration. As a result, the K will increase significantly due to the increased concentration, and the strength and the modulus will decrease as well. The cement product of the Portland, the ordinary OPC, ordinary Portland cement production also yields large amount of CO2 carbon dioxide, which is not environmentally friendly. So to solve this problem, we developed two inorganics and three organics enhanced vertical barrier materials. The number one is and number five are inorganics enhanced vertical barrier material. Number three, number four, and number five are polymer, organic polymer enhanced soil SB backfills. Or no, SB backfills. So number two and number one are proposed to contain heavy metals not in groundwater. And number three is to contain organic acid not in groundwater, to contain bauxite liquor and then fill leachate impacted groundwater. So number four is proposed to contain phenol impacted groundwater. Phenol is a dissolved organic, which is frequently detected in groundwater at pesticides contaminate sites. Number four is cementitious backfill, which has a relatively high strength. It's proposed to contain heavy metals not in groundwater. Let's look at the first backfill. For the first backfill, we use sodium hexametal phosphate, which is called SHMP, we use SMP to amend the sodium activated calcium bentonite, which is a local bentonite in China market. We amend that one and then use amended bentonite and sand to make up the SB backfill. We permit the backfill using the lead with the lead nitrate solution. What we find is that when the SHMP content is up to 1 or 2%, the K will be lower than the commonly used value, T-9. However, for the unamended backfill, their K will be larger than T-9. Also, we permit the backfill with the seawater, the diluted seawater and seawater as well. We find with the increase in the ionic strength, the amended backfill, they display relatively low Kc. I mean very lower Kc than T-9 meter per second. However, for the unamended, the K values are larger than T-9. So why this happens is due to the more dispersed structure and the more negative zeta potential of the bentonite as validated by the SEM photos. I'm not going to say it in details because time is very limited. Let's look at the second polymer, backfill. We use sodium polyionic cellulose called PAC to amend the bentonite, and we make up the SB backfill using the amended PAC amended bentonite, and the sand. We permit the backfill with the lead nitrate solution. We find for the amended backfill, the K remains almost unchanged. However, for the unamended backfill, the K is much higher than 10⁻⁹ meters per second. The mechanism is attributed to the 3D network and pore feeding by the PAC hydrogels. So you can see from the SEM images. Also, with the PAC amendment, the bentonite, the zeta potential of the bentonite will be more negative. That means the diffuse double layer has been expanded due to the PAC amendment. Let's look. The third one is a composite polymer amended backfill. We use PAC and another hydrophilic polymer is called HPMC to make a composite polymer amended bentonite. Again, we use the modified blood loss test to optimize the mass ratio of PAC to HPMC. Here, the x-axis is the water ratio of the bentonite built cakes. The y-axis is the K. The Kc. The testing liquid is cadmium nitrate solution. We find with different PAC against HPMC ratio, we were going to have different Kc values. However, at the given water ratio, this ratio will yield the lowest Kc. So the PAC against HPMC ratio was finally optimized. We use that optimized ratio to amend the bentonite. Again, we use amended bentonite and the sand to make up the SB backfill. We permit that backfill with the acetic acid latent groundwater. As you can see, here the amended backfill. Here the original unamended backfill. Again, we find the amended backfill has relatively low Kc. However, for the unamended backfill, when the concentration of the acetic acid increases, the Kc of the unamended backfill is higher than 10 minus 9 meter per second. Interestingly, what we find, so in summary, the good Kc for amended backfill, but the poor Kc for unamended backfill when exposed to acetic acid latent groundwater. Interestingly, we also find a different morphology in distilled water for single polymer and composite polymer. For single polymer, PAC alone or HPMC alone, we find the polymer morphology, they form a relatively loose structure. However, for the composite polymer, they form dense structure. I mean, the dense structure of the composite polymer hydrogel. So that will be the reason why the composite. Also, we compare the amended backfill with the other types of backfill. Say, for example, the MSB backfill and BPN amended SB backfill. We find our amended backfill that have comparable Kc with the other types of polymer amended backfill. So what is the reason why it happens? We tested the pore size distribution of the backfill. Interestingly, we find the amended backfill have much lower, they have much higher micropore as compared with the unamended backfill. Even when exposed to the acetic acid, the micropore of the amended backfill, the volume of the micropore is higher than that of the unamended backfill. The morphology of the polymer that slightly changes in the presence of the acid condition. Here is the morphology of the polymer in the distilled water. However, after exposure to the acetic acid condition, the morphology is slightly changed, and the structure of the hydrogel is a little bit relatively loose. That means some polymer has been exhausted due to the exposure to the acetic acid. Recently we use the composite polymer amended GCl. We permeate that GCl with the bauxite liquor. What do we find in the PAC amended, the composite polymer amended GCl? They have lower Kc value. That means lower than most of data are lower than 5, 10, and minus 11 meter per second. However, for the unamended GCl, the K is much higher than the commonly used value. And that means 5, 10, minus 11 per meter per second. We also use the landfill leachate to test the Kc of the amended backfill. As you can see, the composite polymer amended SB backfill has the lowest Kc. The PAC alone, that means single PAC amended SB backfill, the Kc is moderate. For the unamended backfill, the Kc is highest and even higher than the 10 minus 9 meter per second. Thirdly, fourthly, we develop a new modified SB backfill, which is called hydrophobic TMA and hydrophobic CMC. This is a modified SB backfill. Why we use TMA? Because TMA is hydrophobic and its absorption against tolerance is relatively high. Why we use CMC? Because the CMC modified bentonite has very good chemical compatibility as exposed to heavy metals. We use that one to modify the bentonite, and then we use the modified bentonite and sand together to make up the backfill. We permit the backfill with phenol solution. We find the modified SB backfill, the Kc is 8 minus 10 meter per second, whereas the unmodified SB backfill for the Kc for the unmodified SB backfill is almost comparable. That is 610 minus 10 meter per second. So the Kc is much lower. Since the Kc is lower, both backfills Kc is lower than 10 minus 9 meter per second. However, the Kc to Kw ratio for the modified backfill is a little bit lower than the unmodified backfill. We also run diffusion tests to evaluate effective diffusion coefficient and partition coefficient of phenol. Here the testing apparatus. Here the SB backfill, and here the source solution containing phenol solution. Here the receipt initially containing distilled water. So due to the concentration difference, the phenol will migrate from the source solution to the receptor driven by the diffusion process. We also measure the source solution periodically, and also we measure the concentration in the receptor periodically. Finally, we use the Plute program to back calculate the D dash and Kp. Here the one-dimensional diffusion absorption equation and the boundary conditions imposed by the finite mass boundary condition as the upper boundary condition, and the lower boundary condition represented by a fixed outer flow boundary. In the Plute program, we back calculate the D dash and Kp. Interestingly, we find the D dash for the modified is almost the same with the unmodified backfill. Here you see the D dash is 4. Here D dash is 3, 10 minus meter squared per second. However, for the Kp, it's quite different. The modified backfill, they have a higher Kp than that of the unmodified backfill. So Kp increases by almost 3 times. That means the retardation fact, that means the absorption capacity has been enhanced. So we also run a number of numerical modeling using the Plute program to figure out what is the cumulative mass of the phenol that comes across the wall and then migrating to the river downstream. So that is one thing is concerned, that river is receptor. So we need to calculate the mass of the phenol that enters into the river. We run program, we find for the for the modified backfill, the cumulative mass of the finial is much lower than the unamended backfill. For the breakthrough time in terms of T10, breakthrough times, that means the time to break through the vertical barrier. So in terms of T10, or you can also use T50 as well. So what we find, the breakthrough times has been elevated by 10 years to 40 years, depending on the thickness of the barrier and depending on the hydraulic gradient of the in the aquifer. Yeah. So fourthly, we propose the soil magnesium activated slag bin and backfill. We use reactive magnesium to active the slag, and then we together mix it together with the bentonite, and then with the local soil. I mean, local soil is sand to make up the backfill material. We compare the hydraulic conductivity in distilled water or tap water with the OPC-based material. So OPC is ordinary Portland cement-based material. Interestingly, we find for the OPC-based barrier material, the K is higher than the MSB-based barrier material. And the pH of the OPC-based material is slightly higher than that of the MSB-based material. When we permit the sodium sulfate or the lead and the zinc mixed contaminant solution, we find for the OPC-based material, the hydraulic conductivity is higher than 10-8 meters per second at the current time of 28 days. However, for our MSB-based backfill, the K is lower than this threshold value. For the contaminant performance, we also need to evaluate the solute transport parameters, including the reduction factor, or D, the D dash, and sometimes the membrane behavior induced, the chemical osmosis membrane behavior coefficient omega, we call that one. So what is the concept of chemical osmosis? Here the barrier, here the solute, here the clean water. So the solute will move from the left side to the right side because of due to the concentration difference. They move, they migrate, driven by the diffusion process. Simultaneously, the water molecule in the low solute concentration, that means the water molecule has high water activity, they were going to move from the right side to the left side due to the chemical pollution difference. So the movement of the water molecule is called the chemical osmosis. For the chemical osmosis, one indicative parameter is called chemical osmosis membrane coefficient. Yes, omega. For the diffusion process, the indicative parameter is D dash effective coefficient. When omega, generally omega varies from 0 to 1.0. For in the case of omega equals to 0, that means the barrier will lose. There's no that means the that means there's no the chemical the cation will move easily from the left side to the right side due to diffusion process. However, if the omega equals to 1.0, it is perfect. That means the barrier shows a perfect membrane behavior. That means all of the cadmium or ions, they will not move across the barrier due to the chemical osmosis. So to evaluate the chemical osmosis and D dash and RD, we use a rigid wall cell, which is a closed system. This testing paradox has been developed by Shackfeld and Professor Shackfeld and Professor Moses. So we use that one to test the lead or zinc solution. We find for the unamended SB backfill the omega the chemical osmosis efficiency coefficient decrease with increasing concentration. The amended SB backfill has relatively higher omega value which is higher which increased by almost 3 times. For the GCL, the omega value is lower than the polymer modified GCLs. For the D dash value, we find for the unamended SB backfill, they have relatively high D dash value. However, for the SMP and PSC amended SB backfill, the D dash value is lower than the amended one. For the GCL, unamended GCL, their D dash value generally are lower than the SB backfill. However, if the source concentration is high, the D dash value of the GCL could be higher than that of the SB backfill. For the polymer modified GCL, the D dash is always lower than that of the unamended GCL. We find the RD value, we find our D dash value and omega has very good linear relationship on the semi-log scale. The RD value of the amended SB backfill is higher than the unamended SB backfill. For the MSB backfill, or the change of the omega with C0 is almost the same. Interestingly, we find the D dash of MSB D dash, that means the effective diffusion coefficient, is not sensitive to C0, but we have no idea why. The reason is still unknown. Finally, we apply the MSB backfill to the MSB vertical barrier to the field site. At the site is the industry contaminant site, and the target contaminants is heavy metals and pH. The vertical barrier was constructed using the mixed walls. We used 2 types of backfill material. One is MSB, another is OPC, which is commonly used in China market. The construction method is dual auger deep mixing method. We sampled the mixed wall and sent to a laboratory, and we conducted K to evaluate to see what the difference between the MSB and what the difference and the K value of the MSB and the K value of the soil cement. At the current time of 1 month, almost 28 days, the K value of the MSB, the average K value MSB is almost 10 minus 9 meters per second. For the soil cement, the K value is 10 minus 8 meter per second. After 4 months, with the cooling time of 4 months, the MSB backfill, the average K of the MSB backfills almost 10 minus 11 meter per second. However, for the solid cement, the average K value is 10 minus 9 meter per second. That means the MSB has much lower hydraulic K than that of the solid cement. So moving on to the concluding remarks. 5 novel vertical barrier material exhibit acceptability as exposed to contamination. The SNP and PEC polymer amid the SB backfills possess lower D- and higher omega and RD than the unemitted backfills. The SNP and PEC polymer amid SB backfill have significant D- and C0 and omega C0 dependency. The composite polymer amendment yields lower Kc in containing landfill leachate than the single PEC amendment. The hydrophobic TMA and hydrophilic CMC polymer modified the backfill has superior, excellent performance in containing phenol impacted groundwater. The soil MSB vertical barrier material shows much lower Kc than that of the soil cement. Finally, the challenges and future works are suggested. Though the feasible vertical barrier material to contain acid mining drainage impacted groundwater, this is a very serious problem in China. And also it's very challengeable because the AMD has much lower pH and also contain a lot of heavy metals. PFAS containing is of urgent importance in terms of Kc, D- and Rd. And for Kc, maybe may not be changed because the PFAS, the concentration of PFAS is usually it's very tiny in the contaminated groundwater. For the institute mixed wall, the barriers to contain source zone contaminants with relative high concentration. Say, for example, if TPH contaminant into soil and confining stress together an alter K or change K, and how to, if change, how to solve the problem. The breakthrough behavior of coexisting surfactant and naples across SB backfills, because the surfactant will accelerate the breakthrough behavior. The long-term performance of polymer in backfills needs to be addressed in the future. The cost-effective method to identify windows of barrier in practice should be done to solve the practical problem. All of the information can be found in the reference here in my research guide. Most of the papers are co-authored with professor already. Thank you very much for your attention. And here's my contact information. Thank you very much. Yes, Professor Krishna.
Yeah, thank you so much, Professor Duke. That was very good. A lot of work, and you explained it very nicely. Of course, as you said, I was involved in all these works, but let's see what questions that attendees have it. Maybe Professor Duke.